Hello, everyone, and welcome to another week of cybersecurity weekly CERIAS cybersecurity seminar. Today, I'm excited to introduce Dr. Evan Sultanic. Dr. Evan Sultanic is a principal computer security researcher at Trails of Bits. His recent research covers language theoretic security, program analysis, detecting variability bugs via taint analysis, dependency analysis via program instrumentation, and consensus protocols for distributed ledgers. He's an editor and a frequent contributor to the Offensive Computer Security Journal, Proof of Concept, or GTFO. Prior to joining Trails of Bits, Dr. Sultanic was the chief scientist at Digital Operatives. Evan, please take it from here.
Sure. Thank you. Okay, so Dr. Taram did a pretty good job of introducing me, but within the context of this talk, as you'll see in a little bit, it actually behooves us to take a look at what most people look at when they try and get to know somebody, and that would be my resume. So if you were to look at the footnotes of my resume, you might notice some interesting things. So first of all, it's saying that you can unzip the PDF of my resume, which is a bit unusual. It says also something about it being a Nintendo ROM, and it's also displaying its own MD5 sum on the document itself. So a reasonable person might want to confirm those things. True enough, the MD5 sum is what it claimed to be. You can unzip the PDF, and it has another PDF inside that has something to do with being a PDF in a Git repository. You can run libmagic's file command, and it seems to think this is a Nintendo ROM, so we can try emulating it. And in fact, it is a Nintendo ROM that also prints out the same MD5 sum of the file. All of my recent work has in some way been related to language theoretic security, which is related to parsers, file formats, and detecting bugs in them. And that's what I'm going to be talking about in the remainder of this talk. If you're interested in how I did these file format tricks, almost all of them are piecemeal published in articles within the aforementioned journal POC or GTFO, which is freely available online. I also gave a talk a couple of years ago at Midwinter Nights Con, which I believe the recording is available on YouTube, which goes into further detail about how all of these tricks work. Happy to talk afterward about how all of this works. What is Trail of Bits, besides being my employer? Trail of Bits is a boutique cybersecurity research firm, about 150 or so engineers. We're globally distributed, but based in New York City. Kind of unusual in the space in that we do a lot of basic research funded by the same sorts of funding agencies that fund places like, or academic institutions like Purdue. And we also have a commercial side, which does security engineering, where we are embedding our engineers in with companies to help them make more secure software from the get-go. And we also do security assessments where companies will come to us, give us their code. We find all the bugs in their code and then give recommendations on how to fix it. And the idea here is that we use our basic research and our funding from places like DARPA and ONR to develop open source tools that then make our security engineers more efficient at doing their jobs. So one such tool that we created, so this was funded by DARPA on the recently completed SafeDocs project, is a tool called PolyTracker. So PolyTracker is an LLVM instrumentation pass that adds so-called universal taint analysis to the program it is instrumenting. So this allows us, after the fact, to reconstruct all of the data flows through the program across all input bytes, from inputs to the program to outputs from the program. Free and open source, you can try it out right now on GitHub. So PolyTracker is novel in the sense that other taint analysis tools like DFSAN used to max out at I think 2 to the 16 bytes of input that it could track at once, and there was a recent refactor which actually reduced that to by several orders of magnitude for various reasons. But PolyTracker is capable of multiple orders of magnitude more bytes tracked with very little overhead. So the idea here is you have your program, you compile it using PolyTracker. That produces a binary with PolyTracker instrumentation. You run it as normal. You get your normal outputs from the program, but in addition to that, you get something that we call a TDAG, which is a runtime artifact that contains all of the data necessary to do post-processing with PolyTracker to extract the data flows from the instrumented program. And you could alternatively also start from a closed source binary, lift it to LLVM-IR using a tool like Trail of Bits remil, and then go on with PolyTracker from there. So in order to achieve this, we extended the SIMP-IL operational semantics for taint propagation to maintain provenance of all of the data within. So typically with taint analysis, when you're using it for a use case like fuzzing, for example, you may only care whether or not a specific byte is tainted, not from whence that taint came. In the use cases that we'll be talking about in this talk, we actually need to know exactly what input bytes affected a given location within the source. So we need to extend the operational semantics for that. I don't need to go into details for that. If you're interested, we have a paper from IEEE S&P Langsec last year that goes into the details on that. But that directly influenced this data structure that we call the taint DAG, or directed acyclic graph, or TDAG for short. Okay, so here we have a really simple program that reads 2 bytes from a file. The TDAG starts off with root node for every input byte to the program. We call these canonical taints. Then we create a new node within the TDAG every time something operates on those input bytes. So here we have foo is reading byte 0, bar is reading byte 1. And then if we have a new variable that is mixing those 2 taints together, we create a new node that branches off from the 2 sources that influenced it. Also, we keep track of which variables influence control flow, and we also record that in the TDAG. And of course, this becomes a giant graph, but we are able to do efficient post-processing on it to do a number of things. So I'm going to talk about 3. So, okay, we have this hammer of data flow analysis. What can we do with it? I'm going to talk about 3 different use cases. The first being reverse engineering. Okay. So in order to get into that, I want to briefly mention a sibling tool, also open source on GitHub, called Polyfile. You can think of it like a combination of libmagic, like file identification, plus a little bit of binwalk, plus basically Polyfile can do a parse of almost any file format while maintaining lexical information. So you end up with a syntax tree that is annotated with the byte offsets for each of the terminals in the tree, or the nodes in the tree. So we can combine that with the data flow analysis we get from Polytracker. So Polytracker will give us this mapping of well, one of the things we can get from Polytracker is a mapping of what input byte offsets each function operated on. So here there's a function ensure solid xref, and that operated on those 2-byte offsets. Format object operated on those byte offsets. Well, we can use what we know from polyfile on the specific input file that was fed to the instrumented parser to then annotate what portions of the syntax tree or the parse tree each of those functions operated on. So we can conclude that ensure solid xref, it operated on the trailer and the xref parse tree nodes, and format object operated on object and dictionary parse tree nodes. But how do we know which function? So uh, there could be many functions that operate on those nodes. How do we know which function is most specialized for operating on that specific parse tree node? Well, we developed a technique based upon information entropy to determine the most specialized functions that sorry, the functions that are most specialized on each type within the parse tree. And we have a paper also from IEEE S&P Langsec workshop on this. The result here, there are two different shapes of node here. The rounded nodes are semantic types within the file format. So these are the nodes within the parse tree, the node types. And the square or the rectangular nodes here are functions within the program. So here we instrumented libjpeg with Polytracker. We did our data flow analysis. We combined it with the annotated syntax tree from polyfile. Used our information entropy approach, and that gave us this mapping between the semantic types and the functions most specialized to operate on them. So here we can see that the JPEG core output dimensions function in libjpeg is most specialized for operating on image width and image height. Makes perfect sense, and so on and so forth. So the thing to emphasize here is we're not doing any sort of string or symbol analysis. This is completely based on data flow and the control flow and structure of the program. So you could take a program with no symbols or obfuscated symbols and immediately be able to tell which functions serve what semantic purpose. Okay, the second use case I'd like to talk about is a term that we have coined blind spots. So in order to introduce what blind spots are, first I have to introduce a term that predates it called file cavities. So this was a term coined by Ange Albertini that is unused space in a file format that is created due to the structure of the surrounding data. So examples of this would be when binary file formats have some unused space for future features. The example I have here is that the Ruby programming language has this cursed feature where the dunder end token will cause the parser to immediately halt and ignore everything after it in the file. So effectively, everything after that dunder end token is a blind spot to the parser. You can put whatever, sorry, not a blind spot, a file cavity. You can put whatever you want afterward, and it will be ignored by the parser. Blind spots, however, are a generalization of file cavities. So they are regions of input that can be arbitrarily modified without affecting the program's output. So unlike file cavities, which are dependent on the file format specification, blind spots are dependent on the program invocation, the program implementation and the program invocation. So I'll give some examples. So the JPEG file format has support for the EXIF format embedded within it. So EXIF is used for storing things like camera model and settings and metadata about the camera, what the focal length was, what the aperture speed was, things like that, and like geolocation data. If you have a program that converts JPEG to another format that doesn't support EXIF or doesn't support any of that metadata. So for example, if you're converting a JPEG to a bitmap, that program can completely skip over the EXIF section. So you could put whatever data you want inside of the EXIF section, and it won't affect the behavior of your JPEG to bitmap conversion program. So that EXIF data would be a blind spot to such a conversion program. Likewise, if you have a program that only extracts geolocation data from your JPEG images, it's only going to be looking inside the EXIF section. It doesn't have to do any image rendering or decompression or anything like that. So all of the image data in the JPEG is going to be a blind spot to such a program. So why do we care about blind spots? Well, as I'll show you, they can be indicative of steganography. They can be used to embed malware payloads, and they are also indicative of parser differentials. So for example, about a year ago, there was a high-profile bug initially discovered in Google's image editing software, but it turns out that Microsoft had independently implemented the same bug in their image editing software. This became known as the Acropolis bug. So what was happening was when you edited a PNG file to crop it, to crop out some extraneous data, instead of truncating the entire file, the image editor would leave the cropped out data appended to the end of the file, and due to a quirk in the PNG file format, it was still a completely valid PNG. It just had this junk image information at the end of it. So it'd still render as if it was cropped, but what people realized was you could extract the full original image from the cropped image if it was cropped using one of these Google or Microsoft image editors that had the bug. And it was revealed that like many images posted to social media, you could extract the cropped out area and it had sensitive information or embarrassing information in the cropped out area. So that cropped out area was a blind spot to the image renderers. Android has a complex system of different types of binaries it could run. You had APK, but also DEX. Turns out that you could create a polyglot between the two. So a single Android binary that was at the same time a valid APK and a valid DEX. And there was a high severity bug discovered where the code signing validator in Android would validate against one, but then end up running the other binary. So this was a way to run unsigned code on Android. So in that case, the portion of this polyglot Android APK DEX binary that actually got run was a blind spot to the signature validator. Philippe Thun and I created a PDF that was also a valid PostScript file for issue 13 of POCR GTFO. If you render it in GhostScript or GhostView, the PDF content would be a blind spot. And likewise, if you rendered it in a PDF viewer that did not support PostScript, then like Acrobat, it would the PostScript portion would be a blind spot to that program. And just to demonstrate the fact that unlike PDF, PostScript is actually a fully Turing-complete programming language. We have a procedurally generated random maze that would be different every time you rendered or printed the PDF, the little microprocessor inside your printer that interprets PostScript would generate a random maze every time. And also for good measure, it would print out your Etsy password file. But the point here is that the content in PostScript, blind spot to a PDF reader, and vice versa. It's been known for a while that you can exploit the error correction in 2D barcodes to embed a barcode within a barcode. So the inner barcode is a blind spot to the outer barcode when you're scanning it, and vice versa, depending on which of the position markers your barcode scanning library picks up on first. So all of those examples are to try and motivate you that blind spots are almost always indicative of a flaw in the input format, the implementation, or both. So what do we do about it? How do we automatically detect blind spots? We need a formal definition for what a blind spot is. We can do that using the aforementioned operational semantics, the extension of SymPIL. We have universal taint analysis with PolyTracker to do the data flow analysis we need to detect it. So then we can get blind spots, and then we need to evaluate how do we actually know that they are blind spots. Okay, so formal definition of a blind spot, it is the set of all inputs that were not read by the program, and the set of all inputs that neither tainted output nor influenced a conditional that led to output. That's our definition of a blind spot. So based on that, we can take our TDAG data flow artifact from PolyTracker, and we have this neat linear time algorithm for enumerating blind spots, linear in the size of the trace. Okay, so how do we know whether these blind spots are actually blind spots? The problem is we have no ground truth. We don't know what is actually a blind spot, so we need to use some statistical method to try and figure this out. And the way we do that is by doing mutation and then confirming whether that affects the output of the program. So here we have a detected blind spot. For every detected blind spot, we try mutating every single byte within it. If it is actually a blind spot, we should be able to arbitrarily mutate all of those bytes, and it shouldn't affect the output. And then we randomly sample from the other bytes in the file that were not detected as blind spots, and then we would expect the majority of those to affect the output, to either like cause the file to be rejected by the parser or change the output. There are some caveats there because there's potential data dependency that would not be picked up from that random sampling. Okay, so we chose to do this with, or to do our evaluation on the popular MuPDF open source PDF parser. So what we did was we instrumented MuPDF with PolyTracker. We have a corpus of over 1,000 PDFs that were collected from the real world, all created by different PDF distillers and PDF software. We ran them through the instrumented MuPDF. There were like megabytes of blind spots detected in there. Then we took an uninstrumented version of MooPDF. We ran the same corpus through there just to get a baseline. We're just observing what the output of the parser was. But then, based upon the blind spots that we detected, we do two different kinds of mutations. As I mentioned, we mutate all of the bytes within the blind spots that we detected, and then we randomly sample bytes outside of the detected blind spots and mutate them. We pass those mutated PDFs through the parser and get our observations from there. So then we can compare the baseline observation versus the two different mutations. We would expect, if our blind spots were correct, the baseline would always equal the blind spot mutated, the yellowish color mutation, because we should be able to mutate anything within a blind spot. And then we would expect most of the baseline comparisons to the non-blind spot mutations to have caused a change. And that's in fact what we see. In fact, we had 0% type 1 error, not just percent, like 0 type 1 error. In every single case where we identified a blind spot, we were unable to find a mutation of the bytes within the blind spot that would cause the output to be different. And then our type 2 error, once again, due to complex data dependencies, we don't know if it's correct, but it's at least an upper bound of 11% for type 2 error. One thing I forgot to mention, for each of the PDFs in the corpus, we were able to run it through PolyTracker, doing universal tape analysis, tracking all data flow of every byte within the PDF. And for each PDF, that took less than a minute of wall time, which I think is reasonable given this type of the quantity of data that we're tracking. The evaluation part where we're doing the mutation, that took over a month of compute time for this corpus, mostly just because we had to, in order to be statistically significant, we had to generate a lot of mutated PDFs. Takeaway there is it's quick and 0 type 1 error. So what did we learn from this? Like, what was the data we actually got from evaluating this corpus? Blind spots in these PDFs were not uniformly distributed across the file. They tended to be either at the very beginning or toward the end of the file. This makes sense because PDFs, an unfortunate decision among the file format creators is that they don't require the PDF header to start at byte offset 0. You can have arbitrary data before the PDF header, and parser just ignores it. And a bunch of PDF distillers and PDF software exploits that, and they add extra junk before. Why do you have blind spots toward the end? The end is almost always contains a table called, well, it's called the XREF table or cross-reference table. This is a vestige of an optimization from like the 1990s where to make rendering quicker, you could look up the XREF table and that allowed the parser to more efficiently render the PDF. It's not so important anymore, and in fact, it's very easy to mess up the XREF table. And in fact, a lot of commercial software that generates PDFs actually produces corrupt XREF tables to the extent that almost all PDF renderers these days will ignore errors in the XREF table, or just they won't even give you a warning if it's corrupt. Sometimes it will silently, like Acrobat will sometimes silently fix the XREF table, and then if you're closing the PDF, it will ask you to save, and you're like, I didn't edit anything here. Why is it asking me to save? Chances are it detected an error in the XREF table and it's just fixing it. But since it's resilient to errors in it, you can arbitrarily mutate it, which means it's a blind spot. We also looked at the prefixes that occurred most often at the beginning of blind spots. So these are the character or byte sequences that most often occurred at the beginning of a blind spot or the start of it. And in the top 100th of a% of these most frequent blind spot prefixes, we saw a bunch of PDF tokens from the PDF standard, like end obj. You can also see dstream there. So that's the suffix to the end stream token. So what's happening here is the MooPDF parser in almost all contexts, it's reading the end obj token, which is a part of the PDF standard, and it reads the first E and it says, oh, in this context, there's no other valid token that could occur here other than end obj. So I'm just going to skip over the next 5 bytes. Optimization. I don't even need to read it because the only valid token here is end obj. You can replace that ndobj with whatever you want, xxxxx, and the PDF renderer or MooPDF will still render it properly. So this is a bug because it can lead to so-called file format schizophrenia. That is where two different implementations of the same file format render things differently, right? A more strict implementation of the PDF standard might either reject the PDF outright or parse it differently because it was missing the endobj object. So you could produce a PDF that looks one way in Acrobat and another way in MooPDF, for example. We also looked at the semantic context of the blind spots. So what do we mean by that? So mentioned the sibling tool polyfile. We pass the corpus of PDFs through that, and polyfile can give you a parse tree derivation for every byte of the input. Parse tree derivation just being the path through the parse tree down to the terminal for every byte in the input file. So then we can count the number of blind spots that occurred in each unique parse tree derivation to see sort of semantically within the PDF standard which regions of the standard were allowing the most blind spots. So number one here is bytes that are not within the parse tree. So they don't even exist within PDF. This is because PDF allows arbitrary binary blobs to just be put in it that don't contribute to rendering. It allows comments and a lot of flex space within the file that isn't actually a part of PDF syntax. So that makes sense. And the majority of the remainder of them are in PDF dictionaries, which also makes sense. PDFs can contain arbitrary key value pair dictionaries, and a lot of PDF distilling software exploits this to include metadata, like author, modification time, things like that, that aren't actually necessary for rendering. As an aside, this technique could have prevented the acropolis. So in order to demonstrate that, we instrumented libpng with polytracker. We took some acropolyptic images. We identified blind spots. We can pass that to polyfile, which also has an interactive hex viewer. And we can see that there's this huge blind spot at the end of the file that, well, we now know is containing all of the cropped out data. Okay, so we finished the blind spots now. Finally, let's talk about variability bugs. So one specific type of variability bug that you may have heard of is a Heisenberg bug. We've all been there where you find a bug, you recompile your program with the bug symbols, and then the bug doesn't exist anymore. So what we'd like to improve differential analysis taking into account Polytracker's data flow information. So the idea here is you have one input, you pass it to two different versions of the same binary. These could be compiled with different flags or running in different environments. You get two different outputs, and then we want to compare the output based off of Polytracker instrumentation. What prompted this was we had a project working on the National Imagery Transmission Format, which you'll be excused if you haven't heard of it because I hadn't either until it was presented to me. But apparently it is very widely used in like aerial imagery. And it's a container format that can contain images, video, all sorts of different stuff. There is a reference implementation available on GitHub called Nitro. And we wanted to instrument it with PolyTracker to do some analysis on it. But in order to do that, we needed to get it to compile with Clang and LLVM, and Clang rejected it. And we're like, oh, well, why is that? Well, its build system is based on GCC, and it turned out that there was a bunch of undefined behavior in the implementation that GCC was okay with, but Clang just outright rejected. We were eventually able to get Clang to compile the program, but we quickly realized that there were not only differentials between the version compiled with GCC and the version compiled with Clang, but there were also differentials between like debug and release and all sorts of things that you never want to see, largely due to undefined behavior. Because recall in the C and C++ specifications, if your program has undefined behavior, the compiler can basically do whatever it wants. So we developed a technique for registering the two program traces with each other based upon the data flow, so based upon call stack and the data flow of the inputs operated on by each of the functions. So this is tricky because if you have different optimization flags, you get different like function inlining, so your call stacks aren't going to match up. Like you can see on the upper right here, in the release build, there were functions that were optimized out. They were either inlined or just optimized out. But our technique here is able to handle that and essentially diff the two runtime traces. And the thing to notice is that at this point, you can see that this is where the divergence happens. The debug trace completely ends at that point, whereas release continues. So what this data flow information provides us is the ability to look at the last input bytes that were operated on immediately before the divergence, in this case, byte offset 756. So we can open up the file, go to byte offset 756, see what data is stored in the file at that point. We have this constant in there. We can open up the file format specification, search for that constant, and it turns out it is a constant in the image representation enumeration. And if we look at the source code of the reference implementation, they forgot to include this enum value in the enum in the source code. That was causing the divergence because of resulting undefined behavior. So here we were able to take what might have otherwise been a very difficult bug to track down and immediately see where the problem is. Okay, so where do we see this work taking us? This last bit of work on variability bugs, this is an active area of research for us. We're improving the algorithm that we're doing to diff and register the two traces together. Hopefully, we'll get to a point where we can even compare drastically different implementations with each other. We also want to extend this analysis to other notoriously hard file formats to parse, like X509, XML, HTTP. Yeah. Pretty much all of our work is open source. You can contact myself and my colleagues using our Twitter handles there, or There's also a Slack channel you can join for Empire Hacking, which is um, a monthly conference that Trail of Bits hosts in New York, but also virtually. And we are available on that Slack. And there are links to our two GitHub repos. Thank you very much for your time, and I am open to questions.
Thank you so much for the fantastic talk. Audience, please enter your questions in the Q&A panel. I hope this barcode doesn't have the embedded barcode in it.
It does, but I think they should both work.
Cool.
Yeah, I was
They're not malicious.
Oh, okay, cool.
So I have a couple of questions. We can start with that while other people write their questions. I really enjoyed your talk. Great talk. So the input dependent, you said the blind spot detection is somewhat sensitive to some input dependent behavior, right? Is it so that when you have a file, for example, in the beginning of the file, you specify how many bytes you're going to parse, right? So if that's 0, then the rest of the file is blind spot. So is that kind of input dependency, but or what do you mean?
So when I mentioned the data dependencies, that was strictly in our evaluation to try and determine how many missed detections we had in blind spots. So the problem is you have a specific byte in the file. How do you know, like, how can you test whether or not that's a blind spot or to like validate, right? Our data flow analysis says this doesn't look like a blind spot, but maybe we missed it. You can try mutating it, and you might be able to mutate it by itself to be anything, without affecting output. But there might be some other complex data dependency where like that byte will affect output only if 5 other bytes are also mutated at the same time. That's the thing that causes computational explosion, and we wouldn't be able to solve in our evaluation.
So that means your tool might, in theory, but you found 0 type 1 error. In theory, find mark something as blind spot, but it is not actually a blind spot.
No, it's the other way around.
That's
So from our experiments, everything that it marks as a blind spot is a blind spot. I see what you're saying. Everything that we marked as a blind spot is a blind spot, but we may have missed up to 11% of other bytes that could be blind spots.
Okay, so maybe an alternative evaluation would be proving or verifying, like using a verification tool, that some of those blind spots are actually like formally proven to be blind spots.
Mm-hmm.
Okay, cool. So in that case, then you can also use this as optimization, right, for performance or storage or memory space optimization, right? If you detect some part of memory is not used, or some part of storage is not used, then you can compress things or just not load them.
Correct. Yes. So related to that, some other potential use cases that we talk about in our paper, I didn't mention here. You could use this to help with fuzzing to know which byte offsets. It doesn't make sense to mutate in blind spots, so that could potentially help reducing the fuzzing space. When evaluating cryptographic code, you would always expect every output from a cryptographic function to be equally influenced by all of the inputs. So that's another thing that we can do using this sort of analysis.
Yeah, nice.
Okay, there was one question, what are the best types of things to put on a GitHub?
Yeah, I think we need more elaboration on that.
Yeah.
Like maybe in blind spot, like a PDF uh, a Nintendo game on PDF sort of thing.
Yeah.
Yeah, please elaborate a little bit on that, anonymous attendee. What are other possible nails that you can hammer?
So other nails, we've been looking into having instead of doing this broad universal taint analysis where we're tracking everything, to allow the um, the developer to annotate within their own code which taint sources they're specifically interested in. So you can imagine like a macro, you wrap one of the inputs, and then you'll be able to see just where that specific variable influences the rest of the program. There was a question, can you elaborate on cryptographic functions? What about independent memory hard functions where we don't want outputs to be directly mapped to their inputs? So our work with cryptographic functions is still relatively nascent. The only use case that we've looked at so far is mapping inputs to outputs. And one of the yeah, it's likely in those sorts of functions that we might lose track of taint through the analysis, so due to taint explosion. So one of the things I didn't mention was, by virtue of using LLVM for instrumentation, we are limited to um, the code or the LLVM IR that we have access to. So if your program is making use of complex hardware or calling out to shared libraries that were not instrumented with PolyTracker, then we will lose the data flow. It'll essentially be opaque to us. So we'll lose data flow across those calls. Depending on how the cryptographic function is implemented, that could happen. I expect what would also happen is we might just, even though PolyTracker does have orders of magnitude more capability of tracking taint than like DFSAN, we would also likely run out of taint whenever, taint labels whenever you're working with a complex function that's doing the amount of computation that a cryptographic function would be.
So I think in a lot of crypto code, right, you want, for example, every part of the key to be used, right? Otherwise, you lose entropy in whatever output you're generating. So if you figure out that this part of the key is not used, then that's not a good thing, right? So
Yeah.
your
And
encryption is not.
yeah, so and this could also be used to identify sources of entropy. So if you wanted to validate that a nonce should ideally only be influenced by cryptographically secure sources of information, it would be a bad thing if the data flow analysis concluded that there was some user input that was able to influence a nonce.
Yeah. So I think we answered that. The I'm curious about the differences between this polytracker and CodeQL, as I saw and on your GitHub of Trail of Bits GitHub, you have some CodeQL queries in repository. So what are the differences between?
Yeah, that's a great question. So I am not a CodeQL expert. I have used CodeQL before, but I've never actually developed for it or looked too much under the hood. But my understanding is that CodeQL is primarily a static analysis, whereas so it's able to operate on code without having a specific input. Whereas Polytracker requires that you actually invoke the program with a real runtime environment and a real concrete input.
Thank you.
Mhm.
All right. So if there is no other question, then we can conclude the talk. Thank you so much for the great presentation and great Q&A session.
Thank you for having me. It's been great.
Thanks a lot, Evan. Take care.
Thanks.